Slide 1. Electrophysiology of the Heart is a series of slide tape programs developed and produced by the American Physiological Society. This is Electrocardiography, Applied Theory, Part 1. Content expert, Dr. Morton F. Arnsdorf. 2. This program begins a discussion of the application of concepts developed in electrocardiography fundamental theory. We will consider the normal cardiac activation sequence and use the single equivalent vector concept and standard lead systems of the frontal and horizontal planes to interpret cardiac electrical events. This is not a course in clinical electrocardiography, but rather an introduction to concepts useful in the interpretation of the electrocardiogram. 3. Your understanding of the theories presented in electrocardiography fundamental theory is prerequisite to successful completion of this program. Fundamental theory presented two models for the relationship between the electrical activity of the heart and the magnitude and polarity of potential differences detected at specific electrode locations on the body. Part 1 considered this relationship in terms of the distributed dipole model and solid angle analysis. Part 2 formulated the single dipole model and equivalent vector concept. 4. Questions and answers are provided throughout this program to allow you to assess your readiness for the program, your progress during development of the concepts, and finally, your overall comprehension of the material presented. After a question is stated, you must stop the tape while you formulate your answer. Many of these answers require you to make rough sketches or simple drawings. After an answer is explained, you must stop the tape to assess your response. Of course, you should also stop the tape whenever you want to study the visual material. The prerequisite test begins on the next slide. 5. In the distributed dipole model and solid angle analysis, this equation represents the potential detected at an extracellular recording site. Indicate whether the terms listed are spatial or non-spatial factors. Six. The solid angle, omega, represents the spatial determinants of the recorded voltage. 7. In the distributed dipole layer model, each wavefront boundary is considered in terms of its solid angle. What does the solid angle, omega, measure? And what are the spatial determinants of the solid angle? 8. The solid angle is a measurement of the apparent geometry of a boundary created by a difference in the transmembrane voltage between regions of the heart, as viewed from a particular point. The solid angle is spatially determined by the actual geometry of the boundary and the electrode distance from the boundary. 9. To analyze cardiac electrical activity in terms of a single dipole or equivalent vector, reference systems must be established. The lead axes of the bipolar leads of Einthoven and augmented unipolar leads of Goldberger define the frontal plane. The unipolar precordial chest leads of Wilson define the horizontal plane. Make a sketch of this diagram and label the axes with their appropriate symbols and polarity. Indicate the anatomical orientation of the planes. 10. The Einthoven lead axes 1, 2, and 3, and Goldberger axes AVL, AVF, and AVR define the frontal plane. The Wilson leads V1 through V6 define the horizontal plane. 11. In this diagram, a spatial vector representing the electrical activity of the heart at a point in time is projected onto the frontal plane. Sketch the projection of this vector onto lead axes AVL and 2 and sketch the ECG deflection expected in each of these leads. 12. Component vectors are determined by constructing perpendiculars from the lead axes to the terminus of the cardiac vector. This indicates a positive deflection in lead 2 and a negative deflection in lead AVL. (13) In this program, we will discuss the normal sequence of cardiac activation and representative ECG deflections, projection of sequential ventricular activation vectors onto the frontal and horizontal planes and vectorial inscriptions on the planes, and a method for estimating the mean electrical axis of ventricular activation. 14. Your first objective is to be able to describe the cardiac activation sequence in terms of myocardial structures and representative electrocardiographic deflections. 15. An electrocardiogram is the extracellularly recorded sum of potentials generated by the heart over a period of time, propagated through the thorax by volume conduction and detected at a specific electrode location. 16. Most electrocardiographic machines either write in ink or inscribe the signal onto temperature-sensitive paper with a heated stylus. The recording apparatus is calibrated so that 1 millivolt causes a 10 millimeter deflection. Most machines, however, permit various calibrations at 1/2 or twice this standardization. 17. The paper speed is usually 25 millimeters per second, so that one large box is equivalent to 200 milliseconds, and each 1 millimeter box is equivalent to 40 milliseconds. Most machines also permit more rapid speeds. 18. In general, the magnitude of the voltage recorded by the electrocardiograph is a function of the mass of the tissue undergoing activation, since mass usually correlates with the extent of the activation boundary and current density. 19. The sinoatrial, or SA node, is the normal pacemaker of the heart, but due to its small mass does not itself have a visible manifestation on the surface ECG. 20. The P wave, representing depolarization of the relatively large mass of atrial tissue, is the first visible ECG deflection. In this discussion, the representative ECG recording is that obtained from standard lead 2 in the frontal plane. 21. Normally, the atria are functionally isolated from the ventricles by the fibrous annuli. Conduction from the atria to the ventricles is through the atrioventricular, or AV node. During the inscription of the P wave, the impulse enters the AV node. Conduction through the AV node is relatively slow. Its period of activation lags beyond the end of the P wave. Since the mass of the AV node is too small to produce an ECG deflection, the period following the P wave is isoelectric. 22. The impulse then traverses the His and bundle branch systems and enters the terminal Purkinje fibers. Due to the small mass of bundle branch and Purkinje tissues, this period of conduction following the P wave is also isoelectric on the standard surface ECG. 23. The wave front of activation spreads from the terminal Purkinje fibers and activates the ventricular muscle. Activation of the massive ventricular muscle produces the QRS complex of the ECG. The deflections of the QRS are referred to in the following terms. The first negative deflection is termed the Q wave, the first positive deflection the R wave, and the negative deflection following an R wave is termed an S wave. 24. The T wave results from the rapid phase of ventricular repolarization. 25. The entire sequence of complexes and intervals recorded by the surface ECG in lead 2 has this appearance. The interval from atrial activation to the beginning of ventricular depolarization is termed the PR interval. the isoelectric segment is termed the PR segment. The ST segment is inscribed during the plateau phase of ventricular action potential repolarization following QRS depolarization. During this phase, the ECG recording is isoelectric in the normal heart. The QT interval represents the entire depolarization and repolarization process of the ventricle. 26. In standard electrocardiographic notation, deflections greater than 5/10 millivolt, that is, greater than 5 millimeters in standard calibration, are capitalized. Smaller deflections are expressed in lowercase letters. 27. Note also that in the QRS complex, additional positive or negative deflections are primed. For example, R' and S'. Entirely negative deflections are called QS complexes. 28. Given the normal ECG tracing in lead 2 and a series of numbered time intervals, name the myocardial structure depolarized or repolarized during each period. 29. These are the cardiac structures depolarized or repolarized during each period. 30. Given the normal ECG tracing in lead 2 with a series of numbered waves, complexes, segments, and intervals, name each. 31. These are the waves, complexes, segments, and intervals of the normal ECG tracing in lead 2. 32. Your second objective is to be able to 1. Describe selected spatial vectors occurring during the normal sequence of ventricular activation, and 2. Sketch an ECG recording based on a set of vectors projected onto a lead-axis reference system. 33. The term activation has been used to describe depolarization accompanying impulse conduction through the myocardium. In the following discussion, activation refers only to wavefront boundaries that result in electrocardiographically recorded voltages and to their movement in a predictable sequence over a given period of time. 34. Solid angles seen from two precordial recording sites, V1 and V6, may be constructed at any instant during ventricular activation. It was established in electrocardiography fundamental theory that although detailed spatial and non-spatial information is gained from solid angle analysis, the complexity of calculation reduces its practical usefulness. 35. We will consider the most commonly observed sequence of normal ventricular activation in terms of the single equivalent dipole model, in which component and resultant equivalent vectors represent the electrical activity of the heart. 36. During the ventricular activation sequence, the sweep of the equivalent cardiac vector, as it varies in spatial orientation and magnitude, inscribes an apparent loop in space. This loop can be projected onto the frontal and horizontal planes defined by the hexaxial and precordial lead system axes. Time is denoted by interrupting the vectorial inscription at 2.5 millisecond intervals. That is, 4 teardrop-shaped dots would represent the electrical activity for 10 milliseconds. 37. In normal individuals, at 10 milliseconds, the left septal surface is depolarized by impulses traveling through the left bundle branch. In this example, the wavefront proceeds from left to right in an anterior and slightly superior direction. At other times, this spatial vector may be oriented in a slightly inferior direction. 38. The 10 millisecond spatial vector may be projected onto both the frontal and horizontal planes. The origin of the projected vector is at zero potential. 39. This projected vector, in turn, can be projected onto the various lead axes. In this way, the magnitude and polarity of the voltage recorded in any lead can be determined. For example, the ECG inscription in leftward leads, such as 1, will be negative, forming a small Q wave, while in rightward leads, such as V1, the inscription will be positive, showing an R wave. 40. By 20 milliseconds of initial activation, the lower two-thirds of the septum, the apex, and portions of the right ventricle and free left ventricular wall are activated. The several component spatial vectors can be summed to produce a resultant spatial vector directed to the anterior, leftward, and either in a slightly inferior direction, as in this diagram, or at times in a superior direction. 41. The 20 millisecond resultant vector can be projected onto the horizontal and frontal planes. 42. In turn, the 20 millisecond vector can be imposed on the lead axes. In this example, the component vector contributes an R wave in lead 1 and continues the R wave in lead V1. 43. At 40 milliseconds, the septum and much of the lateral right ventricular wall have been depolarized. The boundary also moves through the thick lateral wall of the left ventricle. The larger thickness of the left ventricular muscle mass results in a larger component spatial vector as compared to the right ventricle. Summing the component spatial vectors results in a spatial vector that is projected to the left in the posterior and inferior direction. 44. The equivalent 40 millisecond spatial vector is projected on the frontal and horizontal planes. 45. By projecting these vectors on the lead axes, you should be able to appreciate that the polarity of the ECG recording will be positive in 1 and negative in V1. 46. The 60 millisecond electrical events are produced primarily by depolarization of the thick posterolateral and basal walls of the left ventricle, with a small septal and right ventricular contribution. The resultant spatial vector is directed to the posterior, leftward, and slightly inferior. 47. Projections of the resultant spatial vector onto the frontal and horizontal planes have this appearance. 48. Component vectors in the lead axes indicate a negative deflection in the leftward leads, such as 1, and a positive deflection in lead V1. 49. By 80 milliseconds, ventricular depolarization is normally complete. Note that this loop has a clockwise inscription in the frontal plane. 50. Although only 4 equivalent vectors have been described, remember that the electrical events are continuous. Each instant may be represented by a vector. This is a commonly observed normal sequence of vectors. 51. Make a rough sketch of the ventricles and sketch the relative spatial orientation and magnitude of the equivalent spatial vectors representing 10, 20, 40, and 60 to 80 milliseconds. 52. Your drawing should reflect the following relationships. At 10 milliseconds, a small septal vector directed to the right, anterior, and slightly superior. At 20 milliseconds, a medium-sized septal apical vector directed to the left, anterior, and slightly inferior. At 40 milliseconds, a large vector directed to the left, posterior, and inferior. And at 60 milliseconds, a small vector directed slightly to the left, posterior, and inferior. This is a commonly observed normal sequence of activation. 53. Given this diagram, showing a sequence of vectors in the horizontal plane, sketch the projection of each vector onto leads V1 and V6, and roughly scale the magnitude and polarity of the ECG tracing in each lead. '54. The component vectors for the 10 millisecond equivalent vector would result in a large positive recording in V1 and a small negative deflection in V6. '55. The component vectors for the 20 millisecond equivalent vector would result in a smaller positive voltage in V1 and a large positive voltage in V6. '56. The component vectors for the 40 millisecond equivalent vector would result in a large negative voltage in V1 and a larger positive voltage in V6. '57. Your third objective is to be able to estimate the mean electrical axis of the entire ventricular activation sequence. '58. The mean electrical axis of the QRS is an equivalent vector that summarizes the entire ventricular activation sequence. The orientation and magnitude of the mean electrical axis can be estimated from ECG recordings when two or more axes define a plane. '59. Clinically, the mean electrical axis may be said to fall into one of four broad categories defined in the hexaxial reference system: no axis deviation, right axis deviation, extreme right axis deviation, and abnormal left axis deviation. The area marked no axis deviation includes most normal hearts. The definitions of axis deviation vary in the literature. '60. In this example, in lead 1, the negative deflection of 1/10 millivolt is added to the positive deflection of 5/10 millivolt, resulting in a measurement of plus 4/10 millivolt in this lead. This may be considered the magnitude and polarity of the mean electrical axis as detected in this lead. '61. The mean electrical axis of the QRS is the resultant vector obtained from the component vector in lead 1 and a similarly derived component vector in lead 3. In this example, the mean electrical axis of the QRS would be directed at minus 30 degrees, a left axis deviation. Note that since this simplification sums the entire ventricular activation sequence, information must necessarily be lost. '62. The direction of the mean electrical axis can be much more rapidly estimated by determining the lead in which the net voltage is zero or nearly zero. That is, since the mean electrical axis represents the total electrical activity generated by a single equivalent dipole source, the mean electrical axis must be directed perpendicular to the plane of zero potential. '63. In this example, lead AVL is equiphasic, so the direction of the mean electrical axis must be at right angles to the AVL axis and could be directed either toward plus 60 degrees or minus 120 degrees. Since the recording is positive in lead 1, the vector must be directed toward plus 60 degrees, and there is no axis deviation. If no lead is strictly equiphasic, choose the lead most nearly equiphasic and make adjustments by inspecting the other leads. '64. Given the recordings in leads 1 and 3 and the hexaxial reference system, estimate the mean QRS axis by the inspection method. '65. Since the QRS is equiphasic in lead 1, the mean electrical axis could be directed to minus 90 degrees or plus 90 degrees. But since the component recorded in lead 3 is negative, the vector must be at minus 90 degrees, This is a marked left or superior axis deviation. 66. We have described a commonly observed normal sequence of cardiac activation and its electrocardiographic record. We have used the single equivalent vector concept to interpret the ventricular activation sequence and the vectorial loop inscribed in the frontal and horizontal reference systems. And we presented a simple method for estimating the mean electrical axis of ventricular activation. The post-test begins on the next slide. 67. Given the normal ECG tracing in lead 2 with a series of numbered time intervals, name the cardiac structures depolarized or repolarized during each period. 68. These are the cardiac structures depolarized or repolarized during each period. 69. Given the normal ECG tracing in lead 2 with a series of numbered waves, complexes, segments, and intervals, name each. 70. These are the waves, complexes, segments, and intervals of the normal ECG tracing in lead 2. 71. Using standard notation, label these QRS complexes with appropriate morphological descriptions. 72. Remember that deflections of less than 0.5 millivolt are identified with lowercase letters. 73. Make a rough sketch of the ventricles and state the relative spatial orientation and magnitude of the spatial vectors representing 10, 20, 40, and 60 milliseconds of activation. 74. Your drawing should reflect the following relationships. At 10 milliseconds, a small septal vector directed to the right, anterior, and slightly superior. At 20 milliseconds, a medium-sized septal apical vector directed to the left, anterior, and slightly inferior. At 40 milliseconds, a large vector directed to the left, posterior, and inferior. And at 60 milliseconds, a small vector directed slightly to the left, posterior, and inferior. The direction of the several vectors may vary in normal individuals depending on the mean electrical axis, but this is a common pattern. 75. Voltage deflections are indicated on these QRS complexes for leads 1 and AVF at 10, 20, 40, and 60 milliseconds. On lead axes 1 and AVF, plot the voltages for 10, 20, 40, and 60 milliseconds. Draw the instantaneous vector for each, and sketch the loop inscribed by this vectorial sequence. Each division on the axes equals 1/10 millivolt. 76. From the scalar time and voltage recordings in the two leads, you can construct the vectorial sequence and loop in the plane defined by the axes. 77. Given these ECG recordings in leads 1 and 3 for atrial activation, indicate in which lead the net voltage for the P wave is 0 and estimate the mean electrical P wave axis by the inspection method. 78. The plane of zero potential is in the equiphasic lead, lead 1. The mean electrical axis must be at -90 degrees, since the component of the mean electrical axis in lead 3 is negative. 79. This completes Electrocardiography Applied Theory Part 1. For further discussion of these concepts, proceed to Part 2 of Applied Theory. References for additional study of these concepts are provided at the end of Part 2. This program was produced by the Education Office of the American Physiological Society.